And thank you, everybody. As Ursula said, so I'm going to, my goal here is to, not to be exhaustive, really, and to give you a detailed, step-by-step way of performing these studies, but more to give you a few pointers and have something to kick off a discussion. For that, I will touch on the following points. What are the experiments that you can do to kind of measure resistance? What are the experiments you can do to understand resistance? Then the transitions from in vitro to in vivo. And I will wrap up with a few conclusions. So first, for the measuring resistance, really what you want, the goal here is to have a number. And that number then will allow you to kind of assess the magnitude of the risk. Why should you do that? It's because you're asked to do it. And I just here shown the EMA guidance relevant for that. So you should do that. That being said, there is no single experiment that you can perform that will give you that number. There are two experiments, though, that are very favored by everybody. And the first one is, has already been presented. It's the measurement of the spontaneous frequency of resistance. And that's the first one. And the second one is the resistance by serial passage, something that most programs are presenting. The frequency of spontaneous resistance is the very simple design that's already been presented. So basically, you plate the bacteria on a plate that has the compound of interest. You incubate for usually 24 hours, but you can go higher, a longer period of time if you want to see, sometimes you see different mutants coming up after a longer time. And you measure the number of resistant clone, and then you just do a ratio of the resistant clone over the total population, and they'll give you a frequency. So it seems simple enough, and yet there are a few points that I wanted to bring. First one is that you should first start by determining your MIC in agar and not in broth. There might be a difference there. So that's the first experiment. And then you do the experiment. You usually need 10 to the 10 total CFU, and on a single plate, traditional plate, you will plate 10 to the 9 CFU, so you need 5 to 10 plates in order to do a complete experiment. And that experiment is also going to be performed at various multiples of the MIC. All of that to say that is going to take you quite a significant amount of compound if you want to do that experiment, and you should, again. So bear that in mind. You cannot do that with every single compound that you make in a medicinal chemistry program. Second is that, and it's already been brought up, but I cannot emphasize this enough. The genetic context will matter a lot, and this has been presented before. So you should do that for a single species with many strains, because the different strains will have different mutation rate. And you also should do that with, of course, all the species that are relevant for your TPP. So all of that together makes it that it's quite an experiment that is actually longer than usually you might think, and that is also taking, as I said before, a lot of compound. The last 2 points are often overlooked, and I will spend a little bit of time on them. So the first one is to check the stability. What it means is that once you have selected your resistant mutant, you should streak those clones onto non-selective plates 1, 2, or 3 times, and then restreak again those clones on the challenge plate. And that, in doing so, you will realize that some of the clones will disappear. Basically, the resistance was unstable. A lot of people forget that. But that's actually very important because you need to correct the frequency of resistance that you measured before to a new one. To illustrate that, I used this study that has been published with 3 reference compounds, rifampicin, kanamycin, and nalidixic acid. You see here the MICs of up to 30 clones that have been picked on a plate compared to the parental strain, wild type here, with the MICs of wild type. In orange here, you've got the concentration that's been used for selection. And you see that for rifampicin, after 1 passage, 2 passage, or 3 passage, it's very stable. The MICs are all the same, and they are very, very high, which is, by the way, very, very bad. But if you look at what happens with kanamycin, you see a very different picture. even after a single passage on non-selective plate, the MICs of the clones are back to almost wild-type levels. And this is almost for every clone. And for nalidixic acid, you've got a kind of a mixed bag. So very important, as you see, I mean, you can, some of the resistance that you see on a plate will not resist, will not be stable if suddenly they are not, the pressure is not kept. So take that into account when you do these experiments. So once you've done, the second point that I wanted to stress is that once you've measured your frequency of resistance, you check the stability, you've got a corrected frequency of resistance, then you need to characterize the clones themselves. And usually the characteristics that you should be performing is to evaluate the shifts in MIC. Even if you selected at, let's say, 4 times the MIC, obviously the resistant clones might have a MIC shift much more than 4. And that is usually worse. So you need to evaluate those MIC shifts for each clone, or for as many clones as you can. You should evaluate also the cross-resistance, meaning, especially if you know the target, it makes a lot of sense to see if you, in the process of selecting resistance to your compound, you also selected resistance to an established compound that has the same target. Let's say if you target gyrase, measure quinolone resistance makes a lot of sense. The last point is to evaluate the in vitro fitness, and this is usually performed by looking at the growth rate of the mutants and see if they are impaired. Why is it important? Well, usually it's rather intuitive, but if you select resistant clones that have low MIC shifts, that have no cross-resistance and have their growth impaired, you might be in a slightly better situation than the opposites. Very strong, very high MIC shifts, cross-resistance with a lot of things, and also no fitness cost. So this rather simple experiment, actually, when you have to consider the results, it actually takes a bit more finesse. First, as has been said before, there is no established translation to the clinic. So just what is a good frequency of resistance there's no good answer to that question, of course. So still, there are key questions to consider. And even though, again, we've said that again and again, there is no good frequency of resistance, we all have a lazy brain, and so the number will actually be translated for everybody who looks at your number, and if it's below 10 to the 9, people will usually say it's pretty good. If it's around 10 to the 8, even though we all know that it's not translatable, the number will still impact the brain of everybody who will look at your program. If it's around 10 to the minus 8, passable. If it's above 10 to the minus 7, usually people will think it's bad. And that's when the hand waving starts, okay? There are huge variations. Please, consider it normal. We said that before. When you look at different strains, when you repeat the experiment, there will be variation. It's perfectly normal. So do not average the frequencies. I've seen that a few times, people averaging the frequencies. When you repeat the experiments, you will have different results. It's normal. Do not make an average. Do not compare with compounds that are on the market saying, oh, my compound has this frequency of resistance. It's like that of blah, blah, blah. So it should be good because the compound is used. No. All the known compounds, usually they have lousy frequency of resistance. Okay, the fact that they're being used doesn't mean that they are really bad, but we aim to be better than that. Okay, so that's when you look at just the plain number. Then again, all the questions that I've raised before. Are the clones stable? Are the MIC shifts low? Are the frequencies going down with plating on increasing for the MIC? Meaning if you plate again 10 times the MIC, is the frequency going down? Because if that's the case, you might have just to dose higher. Are the mutants cross-resistant and are the mutants fit? Only when you take all of that together can you start to draw some conclusions. I'm going to just sidestep for one second here. In the experiments that were done in the 40s to look at spontaneous versus induced mutation model, Luria-Delbrück showed and it's very clear that when you select for these mutants, you might be lucky or unlucky, meaning that when you have the culture, if the resistant mutant appeared very early on here, you will end up with a lot of clones that are resistant. Whereas if you're very unlucky or lucky, depending on where you stand, if the mutation appears very, very late, then you will have very few clones. This is the essence of the model of spontaneous mutation model. So what this means is that actually it's perfectly normal, again, when you do the experiment again and again, to have different numbers. Actually, if you were really, if you want to do the experiment right, you should do it like Luria and Delbrück did, which means it's called a fluctuation test, which means to run 20 to 100 cultures in parallel and then do the measurements and treat this table in a mathematical model in order to correctly measure the mutation rate. There is no mathematical solution to this equation. And so you have to resort to, there's a number of programs on the internet that do that. It's obviously very complicated to do the experiment, and it requires a lot of work. So very few people do it. But still, this is just to explain that you have different numbers, it's normal. The second experiment that is usually done is the serial passage experiment. It's basically doing an MIC, and when you have, when you've measured the MIC, you go at half the MIC, sometimes a quarter of the MIC, regrow this culture, and then do an MIC again the following day. So you end up with a curve like this, where you see over passages, the MICs are always going up, and they're always going up. So what you get in the end is the passage number, and MIC shifts. A few points of attention. This is very easy. This is just an MIC, so it requires very little compound. You need to perform the test multiple times. Each time you do the test, the trajectory will be different. And please don't cheat. You know, if you do the experiment in triplicate or quadruplicate, do not average the MICs. It makes no sense. This is a stochastic event, so you should consider each trajectory as an independent trajectory. Perform the test with several species. It's the same point that was explained before. Several species, several strains per species, because the genetic background matters a lot. And use known compounds as comparators. You might want to freeze the cultures at several passages, especially when there is an MIC shift, because you might want to go back afterwards and try to analyze the population and the clones, individual clones that are in there. So again, here it's a bit more, it's not just a simple number, so your brain will not interpret that as easily as before, like good, bad, or passable, but still a few points to understand. The two things that are important is how high can you get? Intuitively, if you can get very, very high, it's bad. And if you get there very fast, it's even worse. So conversely, if you're not moving at all over several passages, you might think that you're safe. The real important point here is that usually what you get genetically is very different from what you get from the spontaneous frequency of resistance experiment. Because here you will have time to accumulate compensatory mutations, and stepping stone mutations that will allow you to reach a space that is different from the space that you had before in the frequency of resistance mutation experiments. All right, so this is very fast. I apologize. Again, cannot go into any details, but I wanted to have a little pros and cons of these different experiments. The frequency of resistance experiment is very easy to perform. It's intuitive, it's quick, and it's very, very common. So you will find easily a lot of comparators. On the cons side, there is no translation, but that's true for everybody. There's a lot of variability, and it requires a lot of compound. The fluctuation test is the Luria-Delbrück test. It's scientifically sound, it's robust, but it's very difficult to perform and rarely done, so you have a few comparators. The serial passage is very easy to perform, it's intuitive, and it's very common too. Lots of variability, it's longer, of course, because you can passage up to a month, so sometimes it's, if you want a quick answer, that's not the right test. These are the only ones I mentioned, but there are many other tests that you can perform, like megaplates and whatever. Here, the pros are a little harder to discern, and the cons are the fact that there is no experience, and so you have very few or no comparator to work with. So in the end, should you do frequency of resistance and serial passage experiments? I would say yes. Because, as I said before, the way to get the kind of mutants that you get are different. And this is a segue to the second point that I wanted to raise with you. It's how to understand resistance. What did you get in that makes the MIC go up? Here, the goal is really to understand what does it mean to have a high MIC. And with that information, you might want to rationalize, now that you have kind of measured the risk, you want to rationalize whether you will really encounter that risk or not. Again, it's something that is required by the guidances, and I've quoted the guidance from the EMA. But there are no given experiment really understand high MIC and understand the resistance. So the approaches that are usually performed are to check influx and efflux. If known, you check the target. And if you don't know the target, then I would suggest to do a sequence of the resistant clones or the resistant mutants, and if everything else fails, to work on the mode of action. So briefly, checking influx and efflux is usually performed by testing the MICs against a series of heterogenic strains with influx liabilities or efflux liabilities. So meaning deletions of the pumps, porins, or the biosynthetic enzymes such as here HLDE, LPTD, TOL, PAL, whatever, that allow the biosynthesis of the outer membrane. And usually what you get is exemplified in this table in the corner. Here, X1 is a compound that have a slight defect, slight liability towards efflux, but really nothing major. Whereas X2 has a strong liability with efflux because the MIC goes down with a pump mutant, and compound X3 is not effluxed but has trouble getting in, as seen in the HLD mutant. These are the kind of explanation that you can get. More importantly, what you should do is get the resistant mutants either from the frequency of resistance or the passage, or even when you do MIC90s, to get those clones that are, if you get a distribution like this, you get high MIC clones, and you want to understand why you have these high MICs. So get those clones and sequence them. Here, you should try to directly sequence the putative targets or transporters, especially if you're considering the clinical strains. You will not do the whole genome sequence because you will not be able to decipher the whole genome sequence. So sequence directly the targets or transporters, either if the mutants are coming from here or if those are clinical strains. The preferred option when you have clones that have been selected is to do whole genome sequence. It's very cheap and fast, so you should do it. Word of caution. First, a mutation can affect the target, as exemplified on the right side, but they can also change the target expression levels, and so or the transporter. So bear that in mind. And the second point is that the whole genome sequence of clinical strain is usually useless unless you do a full-blown genome-wide association study. So meaning sequencing 50 sensitive strains and 150 resistant strains and try to understand what will bring you shifts in MICs. And this is really complicated. If you don't have a fair understanding at that point, I think you're in trouble. But I will point, and there are a number of things that you could do to try to understand more of the global view of the mode of action of your compound. I'm just presenting one very briefly. It's called the TnSeq, and so transposon sequencing. The idea is to create a transposon library pool at very high density and then expose the library to control conditions or challenge conditions. And then count, these are the red bars here are indicating the number of transposon, the number of mutants that you have at each position. And here you see condition A is without antibiotic, condition B is with the antibiotic. And you see in condition B, the first gene here, the mutants in the first gene disappeared. So that means that these mutants have been wiped out by the challenge of the antibiotic. So they are much more susceptible to the antibiotic. So this gene is important for the resistance to the antibiotic. If you do that on the whole genome, then you get a full picture of what your compound, of how your compound interacts with the genome. One example is shown here. This is the number of mutants in an untreated condition. This is with a native molecule, and you see here in TOL-C, so the efflux pump, you see that the mutants that were present disappeared. So it's the situation that I alluded to before. TOL-C is important for the resistance, so the compound is efflux. Okay, great. Here you see that mutations in SBMA, which is an inner membrane transporter, are strongly selected. So that means that probably your compound is going through that transporter. You have an issue here. Your compound is efflux, and it's going through by a transporter. So in this case, the team decided to change the compound and try to optimize it. And what they did was evidently successful because you reduce the liability towards inner membrane transport dramatically. You reduce the efflux, and you can understand what they did because you see that suddenly this transporter here is selected. And this is a CD04 importer in the outer membrane. And so the team here, we can see that the team here added CD04 in order to promote the uptake of the compound. So this is just an illustration to show you in one go, in one experiment, all of the genes that affect your compound, and that can be quite powerful. Still, when you have a better understanding of all of this in vitro, what do you do with this information? Understanding resistance is usually relatively simple. A mutation in the pump, a mutation in a porine, a mutation in a target, or it's very, very, very hard. It's really one or the other. So don't really try to make it more complex than it is. It's either simple or very complex. You oftentimes get mutations in regulators, compensatory pathway, central metabolism, and valve biosynthesis that are very complex to interpret, and they often muddle the picture. And you never get the full picture. So the point that is most troublesome is that there is very rarely a translation to the clinic. I mean, Ursula presented this nice, in her introduction, the nice case about methelinum, for instance. So in some very rare hindsight, do you understand when mutations in vitro do not translate in vivo, or in some cases you know that they exist in both cases. So only some mutations in vitro do we know you will find in vivo. The second point is actually the most important one. You usually get intellectual arguments, and those are really dangerous. Like, okay, my mutation will reduce the resistance because there is reduced in vivo fitness, because there is reduced virulence. Sure, it's a nice argument. And usually, it's hard to buy. Basically, people will always have a suspicion. Predicting reduced resistance because on assumed difference in vivo bacterial physiology, like for instance, this changes the metabolism of my bug. Surely this might impact it in vivo. Like for instance, it allows, the mutation will impact the ability to get peptides, for instance, as a carbon source. And in vivo, surely peptides are not the carbon source. Well, nobody knows what the carbon source is in vivo, right? Especially when you consider all body sites. So these intellectual arguments are nice, but whether they are believable, I don't know. So this is the pros and cons, and I will not really comment that. But just to tell you that whole genome sequence of selected resistant mutant is a must, even at early stage. So you should really do that. The mode of action characterization and resistance of clinical strain, you should really do that at a later stage because this is much more complicated than what you might think. To finish, how to go from in vitro to in vivo? Well, this is the process that we've already done. So basically, it's putting all of this information together and trying to see if everything that you understood by doing the experiments that I alluded to before will translate in the clinic, plus adding a couple of experiments that I would suggest here. One is to try to select or observe resistance in vivo models. And people don't do that nearly enough. And second, to test the impact of variation in regimen of administration. This is something you should be doing also, trying to mimic the in vivo regimen of administration. And then, once you have that, you compile everything and you make a proposal. The goal here is to really propose a clinical regimen of administration. So all of that is usually done at a very late stage. If you have to do that early on, you're in trouble. Meaning, if you really think that you will, at very early stage, that you sure this is going to go fine, I only have to dose at 10 times the MIC or 20 times the MIC and I will be fine. I would suggest go back to the Medchem program. In vivo, so it's intuitively not nice, but most people really don't think it's going to happen because they calculate the frequency of resistance and they say frequency of resistance is 10⁻⁷, and usually the inoculum per mouse is not 10 to the 7 CFU, so it should not happen. Well, sometimes it does happen. Right? Even if you have the in vitro frequency of resistance on 10⁻⁷, you do that in an animal model, and sure enough, you will find the mutants. So try it, please try it. Do a double plating. Basically, from whatever comes out of a mouse, You plate on non-selective medium, and you plate on a selective medium, and you will see. Obviously, you can put chances against your compound, so try to use models where the inoculum can be very high, up to 10 to the 8 CFU, so usually a Thai model. You could also try to use a mixed inoculum of wild type and in vitro selected mutants. This can be very informative. So you have 1 to 100 or 1 to 1,000 mix of your mutant and wild type, and you see if your mutant is really going to be picked up in vivo under treatment. If that's the case, especially if you tell me that, no, my mutant is not going to be virulent, try it. You know, it's easy. Well, it's easy. You should try it. The frequency of resistance that you measured in vitro are probably meaningless. This is an example where the compound has a 10⁻7 or 8 frequency of resistance in vitro, and here you see that at time 0, when you do the double plating, here you got a lot of resistant mutant. So the frequency that you measured in vitro here does not reflect what happens even in a simple model in vivo. Yet the compound works, so it is a dose response. And you see that the compound is really working with managing to achieve stasis. What's really interesting here is that when you give the compound once a day versus 6 times a day, you see a difference of curve, of dose response curve. And this is solely due, when you do the double plating, to the selection of resistant clones. You see the purple circles. If you give the compound once a day, you don't select the mutants. If you give the compound 6 times a day, you select the resistance mutants that are really picking up. So testing the impact of the frequency of administration is really important. And you should try and do that. There are the hollow fiber model that is represented on the top right that is redesigned to do that. The one thing that is very easy is to do time-kill experiments also and look at the appearance or not of your mutants and vary the fold MICs and do a mutant prevention concentration to try to see at what concentration of your compound you can get the frequency of resistance you want. So I will try to wrap up. And as discussion point, I wanted to highlight a number of things that I've touched upon in terms of limits to these experiments. The viability, there's a lot of experimental viability in all of the methods that I've described. Genetic, we've said that over and over. So please be convinced that if you test your compound in E. coli, it will not translate necessarily in Klebsiella. And if you test your compound in one strain in E. coli, it doesn't really translate into all strains of E. coli. It's difficult to sample then which species, how many strains, how to choose also the challenge that you will do. You'd have to do it 4 times the MIC, 8 times the MIC, more. All of that is complicated. This only gives you a partial picture of the chromosomal mutation that we alluded to. And so you're not touching on persistence, tolerance, risks. You do not test obviously for horizontal gene transfer. And regardless of the experiment that you performed, it's always hard to translate a single experiment. It's hard to translate the sum of all experiments, really. So a few take-home messages, and I will leave them for you to read. But resistance is one of the most common reasons to kill a project. So do it. Take time to look at it. There are many options that give you many different kinds of information. Take time to plan, and do not just do frequency of resistance. Putting the information together is often very complex, and if you see a problem in vitro, be very cautious when you then claim that it's not going to happen in vivo. Really? Again, it's hard to translate. So think a lot, think very hard on why you think this is not going to happen in vivo if you have a problem in vitro. Then rescuing a resistance issue via medchem is usually difficult, but bypassing target mutation, clearly that happens. Bypassing also efflux, susceptibility to efflux, that can be done. If you have to overcome an influx liability, then that's more complicated. If you have to overcome something that is not related to the target, then you're really in completely foreign territory. So my last point is that there are lots of efforts that have been done to try to understand and to get more predictive models. And yet there is a lot we don't understand about translation. And so we don't understand what a good or a bad resistance profile in vitro is. So we have to be very humble and acknowledge all of that together. Thank you.